Hi, everybody. Welcome back to Bimbo Mentality, a podcast where we sit down with somebody and learn about all the neat things they do, see if they can think like a bimbo well enough to teach us all about it. My name is Bug. I'm joined as ever by my co-host, Emma. How are you doing today, Emma?
I'm doing pretty great, actually. Feeling good. It's June now, which, like, what the fuck?
It is June. Happy Pride Month, everybody.
Happy Pride. Happy Pride, gay people.
Happy Pride to gay people only. Over in the booth doing producer stuff, it's Rue. How are you doing today, Rue?
I'm good. As you can all see, I got my new Panopticon shirt, which is great because I only had like a dozen of them. And supplies were really starting to run low.
Now you have a baker's dozen.
Yeah, exactly. If I don't wear band shirts every single day, people aren't going to know that I have a sick record collection at home. And that's how I relate to people. So yeah, we're doing good.
If you don't wear band tees every day, how will people know about all the sick bands you're into? We are also joined today by our guest, Helen. Helen is a postdoctoral researcher in mathematics, currently working on computational aspects of differential and algebraic topology. Welcome to the podcast, Helen. How are you doing today?
I'm doing all right. Thank you for having me.
We're very, very happy to have you. I'm very excited to learn all about this topic, and I'm going to just jump in with my first question. What is topology?
Yeah, so this is completely serious. Topology is the study of shapes, but the fancy word is like non-rigid properties of shapes. So one of the main things topologists care about is how many holes things have.
We're jumping right in.
I'm always concerning myself with that.
There's a couple different ways that topologists will talk about this kind of thing. And there's a branch of math that grew out of this kind of question, which is more specifically what I work in. That's called homotopy theory. Yeah.
I know less about that. Mainly my experience with that is sort of secondhand, but I'm glad that it's something that is being investigated.
Yeah, so I was trying to think about okay, what would be a good thing to explain? And I put in my bio, I study computational aspects of algebraic and differential topology. Okay, what that really means in simple terms is computational aspects. The kinds of questions I study are what are the things that in principle can be solved by a computer? So it turns out that actually we know some hard limits to what computers can and can't do. And there's some interesting mathematical questions about the kinds of things computers can solve, which is sort of a surprising thing because everyone is always telling us computers will eventually be able to do anything, right? But we actually know some pretty strict limits on what a computer could eventually do.
I know that hard limits are a very important thing in homotopology.
Okay, moving right along.
Before we kind of go into that, Emma, do you have any knowledge of or experience with this field whatsoever?
More so on homobottomology, but that's really it's a similar field, sort of ancillary.
We have got Rue throwing up her hands in record time. We are not even 5 minutes into this podcast, and already Rue is ready to throw in the towel.
God damn it. Oh my god. I can't with you bimbos. Please, Helen, save us.
Yes, tell us more about computers and stuff.
Yeah, so then I thought, all right, well, the kinds of problems that I study are problems to do with shapes and shapes in sort of all sorts of different dimensions, so higher dimensional shapes. And so I thought, okay, I want to explain maybe a way to think about a shape or way to think about what that might mean, right? Thinking about shapes in higher dimensions.
I do have one thing.
Yeah.
And this is actually kind of insane. So I'm maybe losing some bimbo cred here. So I was on the plane last week reading Scientific American, and I read an article about Königsberg, something in Prussia, were 7 bridges, and they mentioned topology. Is that what this is?
Yeah, so that's actually known as like the first original problem in topology.
Oh my god.
Yeah. A question about the city of Königsberg has 7 bridges, and it was like a fun little pastime that the people who lived in that city were like, oh, is it possible to start somewhere in the city and go for a walk and cross every bridge exactly once and end up where you started? And people tried to do it, and they couldn't do it, and they couldn't figure out why. And they thought, okay, it's probably impossible, but like, how would you prove that it's impossible, right? Like, there's lots of different ways to walk around the city. And so this famous Swiss mathematician named Leonhard Euler, like somebody wrote him a letter and was like, hey, can you like think about this? And he like invented graph theory, which is like a branch of topology, or that's not quite right, but he invented topology basically to solve this problem. And he said, oh, there's actually this like fundamental property about the way the map is drawn that doesn't care about like how big the streets are, how big the bridges are, but the way the bridges connect together, you can't actually go on a walk and cross all of them. So that's an example of a topology problem.
Oh my god, I'm so happy right now. I just like read that literally 3 days ago. That was the first time I'd ever heard of it. So that's great.
You came in so much more prepared than me because I'm still a little bit
For the first time ever, I actually knew something.
I'm still a little bit confused about what the actual subject is. So Helen, tell us a little bit about like what you do specifically.
Yeah, so what I do specifically is one of the difficult things is that math and math research is like extremely, extremely specialized to the point where you need to like study for like a bunch of years and learn all these different tools and techniques to learn how to like do the actual research part of it. And so I think if I try to explain like what is a problem I'm working on, it would take a very long time and it wouldn't really work. And so what I decided I think is a good thing to do instead is one of the main tools that I work on or that I work with is something called a fiber bundle. And there's one in particular that is, I think, a really cool example. There's a lot of really cool pictures, something called the Hopf fibration. So I sent out a photo in like the Discord chat, and maybe we can find a way of like attaching this photo to the episode. I know that this is not a visual medium, so it's a little bit tricky. But I also, this is my first time trying to explain like what it is that I do in any level of detail without, any kind of visual aid. It's quite difficult. So
I'll figure it out. We've attached pictures to the podcast before.
Yeah. So there's this sort of weird picture of like kind of a sphere, maybe. It's got a bunch of weird lines and there's a bunch of dots in the corner, and it's very confusing what it is.
I'm gonna try to like take a description or give a description of this, like for the sake of the listener. What I seem to be looking at, and I'm going based sort of very, very superficially, is it's kind of like the shape of an apple, but it's like see-through and like you can kind of see what kind of looks like would be its circulatory system, and it's like twisted around the core, and it's kind of like the multicolor, like a bunch of different colors, like kind of the colors of the Chaos Emeralds.
Yeah, I think that's not a bad description of what it looks like.
My take on it is that it when I see this, I think of, and they probably are similar in purpose, like illustrations, but I think of the illustrations that would be on the cover of like a math textbook.
Yeah, this is taken from a math textbook. So.
Okay, yeah, sure, yeah.
Yeah.
Oh my god, yes, that's the perfect way of putting it. Like,
yeah. So one of the reasons I wanted to explain what this is I was thinking about like what would be a fun thing to explain on a podcast. There's an episode of the Joe Rogan podcast where he has this like physicist who's like kind of a crank come on and explain what the Hopf fibration is, and all he does is he like puts up an animation that's similar to this and is like, this is really fundamental in physics, and then Joe Rogan just goes like, whoa, and then that lasts like 10 minutes and then they move on and they don't explain anything.
I'm so glad that we have sort of brought him up by name now specifically, because I did, when I first started on this little podcast adventure, describe it to a friend, and she said, and I quote, "This is the left Joe Rogan," And what I'm trying to say is, Rogan, we're coming for your crown, bitch.
Hell
Yeah, I think we can do better than Rogan on this one. So
I think we can absolutely
Okay.
do better than Rogan on this one. So tell us about the see-through math apple.
yeah, so this is a picture that is supposed to, well, there's a couple different things you could use it to illustrate, but I'm going to explain it as a picture of something called the three sphere. So first I have to tell you about what a sphere is. Okay.
It's like a ball. I know that one.
I think I got
Yes.
that one.
Okay. So what is a
Like
sphere?
the Earth. The Earth.
Yeah,
Yeah,
a sphere is like a circle, but it's like three-dimensional.
Three-dimensional.
Yeah, so what we want to be able to do is talk about spheres in different dimensions. So
What?
When you say in
Yeah.
different dimensions, are we talking about like time travel and shit?
oh no, I mean like literally different things. So a circle, if you just picture a circle
Mhm.
is, we call it one dimensional because there's one dimension. It's kind of it's like a line curved around. So that's a one dimensional sphere. The Earth, and we're only going to talk about like the surface of a ball, right? So not like a solid ball that's full of stuff. In the same way that, there's a difference between a circle and a disc. We're going to talk about a ball, but just kind of the skin of the ball. So imagine like a beach ball. That is a two-dimensional sphere.
Oh, okay. All right. I think I get it.
So more generally, an n-dimensional sphere where I can put whatever whole number I want for n. And I know this isn't going to make any sense to you right now, but all of the points in n plus one dimensional space that are a constant distance from the center.
Okay.
I actually, weirdly enough, I don't know that I could describe what I just heard, but I think I get it.
Yeah, so just
I'm
to like
kinda-
really
yeah.
solidify it, if I want to know what a one-dimensional sphere is, what I do is I take two-dimensional space. So imagine like a piece of paper. I say, okay, here's the center. And then all of the points that's the same distance from that center, that's my one-dimensional sphere, and that's a circle. A two-sphere is I take three-dimensional space, so that's the space we live in, so we can picture three-dimensional space. You have one point that's the center of the sphere, and then all the points that are like an equal distance from that form this kind of ball, and that's a two-sphere.
This is really actually working for me.
Okay, I'm glad.
I've been sober for like 2 years, but I feel like I'm smoking weed right now a little bit.
It's working for me. Even I think like it's also blowing my mind because I always thought 2D was like a flat, like a circle was two-dimensional from like video game like you know what I mean, like flat.
Yeah, so the distinction that mathematicians make, or the way mathematicians talk about this, is that we want to talk about the dimension of a shape versus like the dimension of the space it's in, and those can be different because I could take a circle and I could have a circle in three dimensions, right? Versus like having it in two dimensions, and so that's not something that is like of the circle, it's like where the circle is.
Got it. Okay.
Right, so the circle itself is one dimensional. Yeah.
I'm vibing with this. Okay, got it.
I confess I'm a little bit lost. I can't rotate the cube. I'm having trouble.
Well,
Okay.
you only have to rotate. You have to rotate a circle, not a cube. So that's where you're wrong. You're good.
So in true math class fashion, pop quiz, what's the zero-dimensional sphere?
A dot.
Huh?
It's not one dot. So I take one-dimensional space, that's a line. I pick a center, and then all of the points that are a set distance from that center.
Would it just be a line?
It's two dots.
2 dots. Got it.
Yeah.
Okay. Yeah.
Yeah.
I'm with
Okay.
you.
Okay, so that's the that's the zero-dimensional sphere. That's kind of easy to picture. We can picture two dots. The one-dimensional sphere, that's easy to picture. We can picture a circle. The two-dimensional sphere, that's easy because we can picture a ball. So now the difficulty is, how do we think about the three-dimensional sphere? Okay, because like step one, take all the points in four-dimensional space. Okay, I don't have a good blackboard for four-dimensional space. Like I can't think about four-dimensional space in my head. Some mathematicians have, I think, a better intuition for how four-dimensional space works. But it's going to break down as soon as you try to go even higher than that. And there's backtrack
for me here.
Yeah.
Explain to me what like 4-dimensional space even really means.
So when I was a kid, I actually asked my mom the same question because both of my parents were mathematicians at some point. And the answer she gave me that infuriated me was, think about what a dimension is and then add more of them.
Oh,
And
come on.
I
That
was
fucking rules.
I was so angry, but now I'm sitting here and I'm like, I think there's not really a better answer to that question. One way of thinking about it is that the dimension of a space is like how many numbers you would need to describe a point in that space. So along a line, you just need to know how far along the line you are. But if you have like a 2-dimensional like chart, like a graph, a piece of paper, you need to know like where you are in one direction and where you are in the other direction. Another way of thinking about it is like, how many directions are there to go from a particular point?
The thing that always makes me stumble is that to describe any point that I'm aware of, all I need are 3. I need up, left, right, and then forward, back. And that
Yeah.
gets me to all points that I'm aware of how to describe, right?
Yeah, because we live in 3 dimensions.
Right.
Yeah.
Yeah,
So-
this is where this is where I get
Yeah.
tripped up on math in general. I get it, but I don't get it.
Okay, so here's a problem, right? We can't really think about 4-dimensional space. It's very hard. But the shape that I want to describe is 3-dimensional. It's the 3-dimensional sphere. It's just that you can't put the 3-dimensional sphere in the 3-dimensional space we know about. So I want to tell you about a 3-dimensional object that just looks different than the world we live in. That's another way to think about it.
Oh, yeah. Let's go.
Yeah.
Let's do it.
Okay. So let's think about other ways of talking about spheres. So, one thing you can do with a sphere is something called stereographic projection. And this is, I'm sort of lying here, but this is kind of how maps of the world are drawn. When we want to draw a map of the world, we want a flat thing, but the world isn't flat, so we need a way of projecting down all of the things onto a map.
I think there are those who would disagree.
Oh my god, are you talking?
Does algebraic topology have any opinions on the ice wall?
On the flat Earth.
I mean, no.
That's fair.
Is a Mercator projection stereo?
So the Mercator projection is a different projection. So I'm kind of colliding 2 different concepts here. There's different ways of projecting down, and there's different things you want like to preserve in your projections.
Got it. Okay.
Right. But like the easiest one to describe how to do it is the stereographic projection. And the way that works is you pick one point that you're going to lose, and you say, okay, that's like the North Pole. You put the rest of the sphere sitting on like the flat piece of paper. And then you take, for every other point, you draw a line through the top point and that other point, and you see, okay, where does that line intersect the piece of paper? And you like draw that point down on the paper. You have a ball, you remove a point, and then you can kind of flatten the rest of the ball onto the paper.
Oh, is that like, so like for like, yeah, the map of the Earth, is that the one where like it focuses, like you said, the North Pole, and you see like the rest of the world in a circle around it on a flat circle, sort of? Okay.
Yeah, kind of, yeah.
Okay.
So you can do this with spheres in general. I mean, if you take a circle and you remove a point from the circle, you can kind of press the rest of the circle down and unwrap it down onto a straight line in the same way. Then, if you think about going the other way, if I have a line that goes like infinitely in both directions, but I kind of like scoop up those ends and put them together and add one point in the middle, I get a circle. If I have a big flat plane and I gather up like the end of the plane and then I like add one point to like glue everything together, I get a sphere.
It's kind of like when you like take a ball of Play-Doh and then you like rub it together into a big long noodle, and then you wrap the noodle around in a circle, and then you smush it all back together into a sphere.
Yeah, exactly. So you need like one point to kind of hold that smushed thing together to be a circle again. So one way of picturing the 3-sphere the three-dimensional sphere is you take all of three-dimensional space, and then you just add one more point that kind of lives at the end of, like, it's called the point at infinity. So you sort of like, you take the edges of your like infinite three-dimensional space, you gather it all together, and you add a point and you stick it together and you get the three-dimensional sphere. Now, in order to do that, you need to be in four-dimensional space, which we already said we can't picture because it is hard to picture four-dimensional space. But you can think about the three-dimensional sphere as saying, oh, just like all of space and then one extra point. That's not super satisfying, I think, for like what the three-sphere looks like, maybe. I mean, it's kind of useful if you needed to like write down stuff. Yeah, it's a little unsatisfying to picture, I think.
This is okay. I'm pretty sure this is what those prog metal guys are talking about, right? Like,
unironically, I started getting into metal in grad school because when I was working on math, I would just like listen to metal and dissociate into math. Like before grad school, I didn't really listen to metal.
There is a distinct correlation between being a math nerd and being a metalhead.
Yeah.
Oh yeah, it's true.
Okay.
Crystal, if you're listening, I love you.
So this is different. This is a really dumb question, but this is because I'm noticing that like when I said I thought 2D was like flat, and so in mathematics it's different. Like I know at least a few nerdy things, and I thought like in physics at least time is considered a fourth dimension.
Yeah.
So like this is separate, right?
Well, no, it's a similar idea, and it's actually sort of the same idea. The point is that if we think about like all of space and time together as one thing, right? So space existing over time, suddenly now you need four numbers again, right? You need the like forward and back, up and down, right? But then also what time? And so this thing called space-time, which is also a four-dimensional object. But I don't really find that helps me picture what it is.
Got it.
Like,
That's
yeah.
fair. That's fair. Yeah, I'm imagining that like that famous like it looks like something that has a gravity well is like indenting inside space-time view, you know, kind of.
Yeah,
thing.
so that's usually like people are trying to draw a picture where they're like, okay, let's show one of the time dimensions, right? Like they're trying to do some kind of lower, like a picture of something happening in higher dimensions by like ignoring, kind of the same way that you can draw a picture of a three-dimensional thing on a two-dimensional piece of paper. So you can like get pictures of higher dimensional things, except now we're talking about a two-dimensional picture because it's still on a piece of paper of something four-dimensional. And it's like you're losing a lot more when you do that.
Got it. Okay. I'm actually, okay, I'm following. Yeah. Like when I learned how to draw the box, a three-dimensional box on paper when I was like a kid. Yeah. Okay.
So one other tool we can use to understand these things is the thing that they talk about. They talk about at length on the Joe Rogan podcast, or where the dude is just like, these things are so cool, they're fundamental to physics, which he's not wrong, but he just doesn't explain what they are. So it's something called a fiber bundle, or alternately a fibration. Those are slightly different, but for this purpose, they're not. So the idea there is we can build up shapes that are more complicated out of things that are simpler. So a fiber bundle has basically three pieces of information. There's something called a base space. There's something called a fiber, and then there's information about how to glue everything together into a bigger space. Okay, so that sounds really complicated. So let's do a very simple example. So we start with a base space. Let's start with just a circle. Okay. And then the fiber, let's just take like a line segment. And so anything where the base space is a circle and the fiber is a line segment, what we're going to do is at every point of the circle, we're going to like think about an entire line segment instead of just a point. Okay. And then how do I put these together? Well, there's actually kind of two ways. So if I think about taking my circle, and my circle is just a line that's wrapped around to be closed. So I have my line. At every point on the line, I actually have like a line segment standing up. And then I go to close it, and I have two choices. One is to just close it up kind of the obvious way, and I get a cylinder. Other one is to close it up, but to flip the line segment upside down, and then close it.
Hey everybody, producer Rue here. Just a quick programming note right here. Bug's microphone just kind of gave up the ghost for a second, like for a few minutes actually. They were having to kind of troubleshoot while we were on the call. Kind of unfortunately, fortunately, Helen and Emma still had a really interesting kind of conversation, kind of went onto some interesting topics. So I thought about it, decided to leave it in the show. Y'all will hear when Bug comes back. They're not exactly subtle.
I've heard of the Mobius strip before. You have to understand, I ended math at pre-cal, and I was liberal arts major, so this is stuff for me to grasp. I like my special interest is weather, and I couldn't go into meteorology because I was too dumb to do the math. So tragic, I know. I thought it was just chasing tornadoes. It wasn't.
I actually just think that like math is taught extremely badly, and none of the fun stuff with shapes is even like a thing you can know exists until like at least later in college. It's kind of a real problem.
I think about how
Like-
math gets taught really badly all the fucking time. I know this is probably some of this is gonna end up on the cutting room floor because we can't hear from Bug right now. But like high school, I was like literally I almost didn't graduate because of math classes. And then in college, I had a professor who kind of got me to where I was able to do math. And then by the end of college, I was doing an arts program and doing all of my friends' math homework in exchange for free beer because I liked doing it. And I was an alcoholic.
Yeah. Yeah, math is one of those weird things that like instead of just being like, oh yeah, it's tough and it needs to be taught well, or I don't know, there's this idea that like, oh, you just can like be naturally just like stupid and bad at it, and that can
Yeah.
be something you can decide by the time you're 12, and it definitely has nothing to do with like anything, socially happening, or I don't know, it's terrible.
Yeah. No, I just had like a bunch of like mean women who thought I was stupid for not knowing how to do algebra. And they made, the years in which I was going through puberty a living nightmare. And that didn't help. It turns out it's so
Yeah.
crazy. That doesn't help.
Yeah. I had a really good math teacher in high school who like had a job for a while helping people get over math phobia, and she like wrote a book about it, and so she was really interested in like how to like teach people math in a way that doesn't turn them off of it and
Right.
all that kind of thing, and she was super cool. But
When I was reading that Scientific American article, Helen, there was one thing on the topology thing, but there was also another longer article. I think the buzzier headline was like the scariest problem in mathematics, something like that. But basically, it was, I'm pronouncing it wrong, but the Riemann hypothesis and how it's like stumped mathematicians forever, and like we don't even know if it's possible to solve.
yeah, people really like to sensationalize these things because I feel like, I don't know, like it is super interesting and cool, but like people then are like, we need to write like exciting headlines. And so
I
they write these
know.
things, and it's just like, yeah, it's just a hard problem, but there's actually a lot of those. It is a super interesting problem, and it sits at like it like depending on how it gets answered, because it's a question, like it's a yes or no question, and depending on how it gets answered, will have effects on like lots of different areas of math, and it's something people have been studying for like over 100 years, and so it's like interesting that it's like still around, and we still haven't really made much progress on it. And
The one thing I would say about that I thought was so fucking cool, which you mentioned, was I forget the application of it. It was like he was the student of Riemann or the mentor, but was talking to someone, and like they realized like years later that that same like hypothesis had applications in completely different. It was like in astronomy, I think, had completely different, and like it was like almost beautiful to think how like it like underlaid how math like so much natural phenomena like follow mathematical principles underlying it, and I thought that was like incredible.
yeah, it is really cool. There's definitely some really cool applications of it. It's just like those are really hard to explain. I don't know. There's also something about just like the way the kind of math the public gets exposed to. Like people just don't really know what math research is, and then
True.
places want to do like, oh, this is like very cool and exciting, but like I don't know. There's like this weird disconnect. It feels like it's worse in math than like a lot of other fields where like at least the public might not know anything about like particle physics, but you kind of like have an image of like what a particle is, maybe. Like, not that it's a good one, but it's just like no one knows what mathematicians do. Like, even like the
That is
terminology.
very true. That is very true.
Sorry, y'all. I was having some microphone issues, so I lost you there. I know we were talking about fiber. All I know about fiber is that it helps you poop good.
All I know is that I don't get that in my area, so I have slow internet.
Yeah. The rates they're charging for fiber bundles from, is just criminal here.
It's insane.
Terrible.
Not good.
No. Okay. Wait, but I need to ask, like, did this explanation make any sense? So I'll just quick recap. So
Please.
you have a base space, which is just, we're going to start with a circle. At every point of the circle, we're going to like glue on a line segment, so a stick. And then we can either have them all pointed the same way, or we can think about taking our circle and like when we glue the two ends of a segment together to get our circle, we twist one of the sticks and we glue them back. And so now we have this like single twist. You can think about like a band of paper that you've glued together, but you've introduced a single twist in it, and that's a Mobius strip.
That's that. Okay, yeah. So I can picture doing that with Play-Doh. So I figured it out.
Fuck yes.
So the picture that I sent, this picture of the Hopf fibration, is a picture of the three sphere as a fiber bundle where the base space is the two sphere and the fiber is circles.
Okay. Okay. I think I kind of get it.
So we can like slow down and really unpack it. And I think you can describe like how to build this thing and it'll make a lot of sense. Okay. So take the two-dimensional sphere and cut it along the equator. So you have two disks. Now, for each of my disks, I'm going to take at every point, I'm going to associate a circle. So one way to think about the shape you get when you do that is like a solid donut.
I do know a lot about donuts.
How do I glue back together my two solid donuts to get a three sphere? Well, again, it's not going to be something I can do in three-dimensional space because we know that we can't have our three sphere in three-dimensional space. It needs to like live inside a four-dimensional space. But I take my two solid donuts together and I glue them together, like link the donuts together, and then sort of unwrap one of them around the other to try to glue their surfaces together. That's kind of a picture of what's happening here. And you're going to like, one point is going to want to like go to infinity. But that's this picture of the Hopf fibration. If we look at the picture, we can see like what really is happening. There's this sphere. You can picture kind of like a normal two-dimensional sphere sitting inside this apple. Through every point of that sphere, one of these circles is crossing. And the circles are kind of twisting around and filling out this three-dimensional thing. And then there's that one line that's like sticking through the center.
Yes.
That line is actually one of the circles, but it's going to that extra added point at infinity and then coming back from the other direction.
What the fuck?
And so this fills out the three sphere as three-dimensional space plus one extra point.
That's I get it, but it's so weird.
Yeah, so there's like a ton of animations of this on YouTube. You can look it up. And I feel like there is an element to which like, okay, once you've had the explanation, and like there's even a color-coded thing here. So that's what this little like color-coded sphere in the corner is telling you. It's saying you have this sphere. Here's a bunch of points that you can kind of picture. They didn't draw in the whole sphere, but you can say, okay, all those points are kind of sitting on some sphere. And then each one has a different color. And then that color is corresponding to one of the circles that's drawn in the image. So that the point at the North Pole, that like blue point, that becomes that blue, kind of purplish blue line that's going through the center. On the other side, you have the South Pole is yellow. You have that kind of center circle that's going around the middle. And then here's how all the other circles are kind of twisting around to fill out this whole space.
Math is fucking trippy, man.
It is.
And so one of the cool things this guy Hopf managed to show is like, okay, you can do that. You can make the 3-dimensional sphere out of something where the base space is 2 dimensions and the fiber is the 1-dimensional sphere. You can do something similar where you can build the 7-dimensional sphere where the base space is the 4-dimensional sphere and the fiber is the 3-dimensional sphere. And there's one more, and that's it. But like there's some special properties of spheres that are exist in only these dimensions. And so that's the that's the Hopf fibration.
Crazy.
And so these things are used all over the place. They're used a lot in physics because you can, when you talk about something like space-time, you can also say like, okay, I have this like big space-time thing, but actually maybe I want to think about that as like a base space, and these other things I want to study are like extra degrees of freedom. So I want to think about those as fibers. And then this is a really common way of building more complicated structures. You like start with something basic. So in this case, the 2-dimensional sphere, and you say, okay, I want to add kind of the information of a circle at every point. Well, there's lots of different ways to glue that together. So, in this particular case, we're getting a 3-sphere. I guess I could talk more about that, but I'll stop there.
When you say like used to build more complicated structures, are we talking more like theoretical structures there, or does this end up getting used in like engineering and architecture and stuff like that?
So I meant it in the case of just theoretical structures, so things that like mathematicians would study. This stuff is used less directly in applications like engineering, because when we're talking about topology, we're really talking about shapes without caring about like rigid physical properties. So, you've used a lot like, oh, I can make this out of Play-Doh by doing this thing. Like this is something topologists kind of think about, is like, okay, what are the properties of shapes that like you can, when they're made out of Play-Doh, and so they're kind of bendy and stretchy, but maybe you aren't allowed to rip them or things like this, right? Which is different than like what engineers would care about, which is like building a solid structure that's not going to move and fall down.
Sure. So, like, it's crazy. I mean, this is the part that is like I get, but is tripping me up, is just this idea of like theoretical structures in general is neat, but also confusing.
Yeah. So, I guess it's kind of hard to really explain, because one of the things that makes this tricky is like the point in a lot of cases of doing this theoretical math research, like, is the level of abstraction that it gives, right? So I can tell you about all these different reasons we might care about studying something, but those maybe aren't the thing we're trying to actually study, I guess. I mean, what's a good way of putting it? Like, I can tell you about this thing, I can tell you about something called a manifold, right? And I can say, okay, space-time is an example of something that's called a 4-dimensional manifold. But then that might convey that, like, okay, what are we doing when we're studying these things called manifolds? We're studying space-time. But we're not really studying space-time, right? It turns out that, like, the theory of manifolds. And there's all sorts of different reasons why mathematicians study things. So some really are interested in, like, oh, I want to apply it to this particular physical phenomenon or this engineering thing, or this thing in this other field. But sometimes mathematicians are just like, oh, this is a really cool, beautiful thing I want to study. And that was really in a lot of the cases, like the reasons I went into math research and the things that I look at.
Yeah, I mean, we're jumping the gun here a little bit, but I think that's going to be part of what I take away from this session is just, I mean, math is not something that I personally have thought much about since, like, high school, when the point of doing math was to like get my homework done. But it is like, the level of abstraction is interesting because it's just not a way that I am used to thinking and approaching topics at all. So it's neat. It's a whole just different way of thinking about things and the world, and it's neat. It's a neat approach to just thinking about things as like, well, there doesn't have to different shapes don't have to literally, tangibly be real to think about them and have them be real problems to solve. It's just a whole level of thinking about the world that I don't really do much.
Yeah, I was gonna say, I think what's been so interesting to hear you talk about this and everything is like you just said about the different folks that get into mathematics for different reasons, and like I think you can take that in not quite the same, but like, I used the physics example earlier. I feel like there's folks that like get into physics to like, pontificate like the like more abstraction, right? More abstract parts of physics. And there's folks who are like get in there to like apply it, right, to different things. And sometimes those meet. And I think it's really, I'm someone who, I know we talked a little bit about like math education is poor. And so like people aren't necessarily inherently bad at math. I would argue you have not seen my my brain on math test, but I would say like it is really interesting to see how people's minds, I think, are set up like in a way where they like gravitate towards the abstract and the theoretical. And I think that's been really cool too, because I had never even considered like that picture you showed. Like we definitely want to show that to our listeners because it's like something that I didn't even like think about ever, if that makes sense. And that's really cool.
Yeah, I think back to like my high school days when like even then, not thinking about math in these terms, there was the like refrain of like, well, when are we ever going to use this? It's like, can't it just be cool? Can't you just think about things for the sake of thinking about them?
Mm-hmm. Yeah, I think there's kind of two related problems. And I think the easier one to see is like, okay, we get a bunch of students together and we're like, okay, the thing you want to do with your life and your future is going to be like dependent on how well you can, solve a bunch of these problems that we only sort of like not really well explained. And we've insulted you for struggling to understand them. Here is a time situation, solve a bunch of them. And if you do badly, it is because you are sort of transcendently bad at doing this and it has nothing to do with anything else, right? And it's like, yeah, that just really sucks. Like, let's make these really high stress things and say that like actually it's something called like your ability to do math and it has nothing to do with like anything else, right? And that's not to say that there aren't people who are like struggle more with math or who are like more inclined to do it, right? I'm not claiming that like I don't have some like, natural weird inclination to just think about these things. Like obviously I do. That's why I went into it, because I like find this kind of thing enjoyable because I'm strange. But yeah, I don't think that it's like something where like, well, if you're not good at it to start off with, like there's no point in even trying. And I think that's a lesson that gets put a lot in math education. And the other thing I think is that, one of the hot takes that I'm only half kidding, is that I think math is like missorted as a STEM field. I really think math is like a humanities subject because I don't actually think, you can use math to obviously science like uses math, right? And like if you want to do quantitative analyses of things, like you're using math, sure. But like a lot of math research, huge parts of math research are really guided by like aesthetics and what is a nicer way to do something. And I was trying to solve a problem in grad school and I figured out like, okay, I could probably solve it if we went through and exhaustively did this thing. And my advisor was like, yeah, but like a solution like that, like wouldn't be worth it, right? It would be like really painful to come up with. And at the end, the thing you'd get like would be kind of ugly. So let's pick a different problem, right? And that's not something you would come up with if you're doing like, right? You wouldn't do that in another like technical field, right? Like if you were doing a software startup and your boss was like, your boss would never be like, well, the code that would do this wouldn't be nice, so we might as well not build this product. Like that's kind of a weird, you wouldn't say that. Or, we don't want to build this bridge because the calculations involved would be ugly. Like, no, we want to build a bridge, right? Like that's the whole point of doing these things. And I think math has a lot more to do with like studying humans and human understanding in a certain way.
I love this argument. I love the humanities argument and the like. I mean, going back to like sort of when we were tangenting for a little bit about how we keep learning more and more that like everything we observe in the physical world and like even at a cosmic level, like just behaves to the same mathematical principles that we're finding more and more. And I think that's like there's something almost like primal is the wrong word, but like foundational to it that I can totally see what you mean about that.
Yeah, and I think even a step further, like it's not just that like we're going out and we're seeing that all these things are governed by the same laws. It's like we understand that actually the reason there's similarities is partly because these things work the same way across all these different scales, but also partly because like this is how we like to understand stuff, right? Like you could imagine a different way of understanding like how physics works and how all these things work. And it's sort of not an empirical thing that the models we build, the mental models we build for how to understand stuff, right? So throughout this, I've been telling you about like, okay, the point of this was just to understand what is the three-dimensional sphere. Like the three-dimensional sphere didn't change at all in the different explanations. And the thing that motivated like the different explanations I came up with were, what are the ways, what is a satisfying explanation? Like what is a good way to explain what a three-dimensional sphere is? Because I could tell you, yeah, four-dimensional space. So a space described by four numbers. And then take all these points, right? And here's a description. And it's sort of like, in some sense, a perfectly precise description, but it's like totally uninteresting and unsatisfying. And like the interesting construction was, how do I actually tell you about it in a way that like makes sense to you and that you like think of as understanding it?
I do want to say too, like while we're sort of on this subject of, you know, math as kind of an art, that like this picture that we were just trying to describe is, you know, that we were using these math concepts to describe is actually quite beautiful. Just this shape, like the way, you know, it's the way that you look at it, you can look at it kind of at different points along the sphere, and the whole sort of shape and build of the object looks different. The way that the, you know, entire shape of it is suggestive of something, you know, very kind of cosmic, but also shapes that are kind of more familiar. I mean, it despite it being something that is supposed to be describing something we've never heard of, like there's a real artistic beauty to it.
Yeah, and like I don't know if you guys experience this the same way, but like I think it's really cooler when you like know what it's trying to say, right? Like when you first look at it, it's like, yeah, there's just a bunch of squiggles. Like the colors are pretty, but something about like the object it's encoding and understanding like, okay, this is giving me this kind of picture of something that I don't really have before this, the intuition and the tools to think about, you know, but now, okay, I kind of have these like tools I'm putting together and I can get this picture of something that like previously I just had no way of picturing. Like, I think that's really cool. And it's sort of an artistic, like aesthetic experience as opposed to anything else.
It's an artistic depiction. Literally the point of this as an artistic depiction is to like depict a shape that we can only conceptualize of. That's really cool.
Agreed. I'll admit, when that image was submitted, I definitely thought just like, oh, that's a pretty thing with a lot of colors in it. And I like that because I like colors. And like, yeah, I think I didn't grasp it until hearing you talk about it. And
yeah, I think it's it is sort of a common thing that like math illustrators will do. Like sometimes people will just be like, oh yeah, look at this picture, it's really cool. And like that's exactly what they did on the Joe Rogan podcast. They put this like impressive thing. It was a slightly different picture, it was a different animation, but they just like put this animation on of this thing twisting around, and they were like, whoa, isn't this so mind-blowing? And it's like, well, it's not really mind-blowing. I mean, you're just looking at colors move on a screen. Like you're literally watching, like, this could be a TV show for babies. It's literally just like colors moving on a screen, and you're not saying anything about what it is. So you're literally like a baby with jangling keys, and you're like, whoa, this is blowing my mind. And it's like, no, that's not really the point at all, right? But it becomes interesting when you're like, oh, I can see what is actually happening here, right? Like I actually have tools to understand, like, here's what is being said.
At least once per day, I am the baby looking at the jangling keys.
I mean, same, but...
Listen, jangling keys can be quite fascinating. I love distracting myself with Play-Doh.
Hell yeah.
I was a big Silly Putty fan as a kid, for sure.
I don't know that I have ever in my life actually like encountered Silly Putty IRL.
What?
I just completely
That's
missed
crazy.
Silly
What?
Putty.
You didn't ever like push it down in like a newspaper and like get the ink on the Silly Putty? That was like the coolest thing to me.
And it
No,
came in
I
that
don't
little
think I ever
egg.
did that.
Oh my god, that was such a
Yeah,
fun
the little
toy.
egg, and you got to like break it apart and then put it back. Oh my god, I can't believe this right now.
Yeah, the more that you're describing it, the more that I realize that I don't even know that I could like that I even know what Silly Putty looks like.
Do they still make Silly Putty? Is there somewhere I
They
can
have
go
to.
to get Silly Putty? I want Silly Putty.
I think I think they definitely have to. It's one of those things where like I think things don't exist anymore, and it's because like
because like we're not the target demo for Silly Putty, so they're not advertising it to us.
Yeah, well, that, but also like commercials for kids cereal, right? As a kid. Okay, wait, sorry, go ahead.
You can go to Target and get a 4-pack of Crayola Silly Putty for $4.99.
Incredible.
Right now. So
I love it.
There's an advertisement for Silly Putty on our podcast.
Yeah, Silly Putty, get in touch.
If you want to give us the dosh for that, please.
Wait, Bug, did you? Okay, so now Bug's gonna be like, I never played with like the bouncy balls either. You know the super balls that like you would like get a room with a bunch of like solid surfaces and just throw the ball as hard as possible and then duck. You know what I'm talking about? No,
I don't think I ever did that either.
Bug,
you never. What?
Did you even have a childhood?
What?
I am, in fairness, the baby of this podcast.
Oh, yeah.
Oh my god! But okay, the bouncy balls have been around forever. It's just a bunch of rubber and you throw it.
Are we just talking? I mean, are we just talking about like balls as a concept? Because I
No,
know,
like the really bouncy
to be clear,
ones.
we're talking about like
they're like
toy.
They're just like concentrated rubber in a little ball, and you like they have like insane bounce ability, and you just like throw them on something, and they'll just go.
Oh wait! Oh no! I do remember that. Yeah, no, I did.
Good.
I did have one or two of those.
Phew. Okay. It's about to be like, what?
We will. Here's the thing. Here's what's gonna happen. Bug, I know recently we were joking about the Bimbo Mentality live roadshow spectacular, where we would all pile into a van, drive around this great country of ours, and do Bimbo Mentality live shows. There will be a Silly Putty
Silly Putty demonstration. Just to be totally clear on this, not even remotely viable right now, but I would love to do Bimbo Mentality live. Let that be an exclusive. If that ever becomes a possibility, I would love to do that.
Make us famous, make us rich, so that we can do that. Because right now I'm like struggling to take a 3-day weekend off at work. So
yeah. Anyway, we got off on a big tangent, and I think a very valuable tangent there about like math education and how that works. We are kind of nearing the point where it's time to wrap up this podcast. I am sure there is many, there is much more to talk about when it comes to this particular subject, but I think we got a very neat little education into kind of understanding how algebraic topology works as a concept. I think we can go ahead and move into our little what we learned today segment. Emma, what'd you learn today about algebraic topology?
Oh gosh. I think I learned to like some it's already breaking my brain. I think I learned like more beauty in mathematics and a better appreciation for something that was very like dense and unknowable for me. So that was my serious answer.
I learned about uses for fiber other than taking big dumps. I learned about the importance of hard limits to homotopology. I learned that there are shapes that only exist in your mind. And and I learned what I really I don't know that I am coming away in this moment with like a deeper understanding of algebraic topology. I don't know that it totally clicked. I don't know that I totally got it, but I learned how to like I learned a little bit about like how to be curious about this topic. I am going to be, when I listen back to this podcast to, take notes for editing and stuff like that, I am going to have this picture that we just discussed in hand, and I am going to take another stab at understanding this, because even if I don't get it, even if it's not clicking, I think I'm curious about it. I'm interested in it. I had a lot of fun learning about it, and I think it's really neat. And that's Bimbo Mentality, baby. Helen, having heard what we learned today, how do you think you did? Do you think you were successful in thinking like a bimbo enough to teach us about algebraic topology?
Yeah, I think I'm pretty happy with that. I think there's basically two very, very minor corrections that I just wanted to make sure I said. It's like the pedant in me. So one is, it's not homotopology, it's homotopy theory. And two, I didn't get into this at all, but just because if there's anybody listening to this who knows, there actually is something called a homotopy limit, and it's different than a regular limit. It's a little bit weaker as a concept. Yeah. Okay. Otherwise, yeah, I think that's pretty great. I'm pretty happy with that.
Awesome. Before we wrap up today, Helen, I know you have a few things you want to plug?
Oh, yeah. So if you liked listening to me explaining stuff, I have another podcast that is entirely not about math. It is called Odium Symposium, and it's me and my friend Sarah, and we try to understand, like, the tagline for the show is it's a podcast about the production of bigotry. So what we do is we like find a bigot or a bigoted piece of media or text, and we like dig into it, and we understand, like, okay, why does this exist? Like, why did this person make this? Like, what is it doing? What is the sort of role of that? Yeah, and we have a Patreon, so you can find us on patreon.com/Odium Symposium. And then I also have a blog that I haven't updated in a while, but it's got some writing on it that I like, some fiction and nonfiction that I've written, and that's on bananasinwartime.ghost.io.
Awesome. Well, it was great having you on. It was great learning about your subject. Little programming note on the last episode, we ended saying, join us next time to talk about competitive shooting. That's what we'll be back to talk about next time. Just a little scheduling flop. But we will be talking about that soon. I also want to mention, because I have not mentioned it yet on the podcast, that Bimbo Mentality is now managing an old-fashioned internet forum. So if you would like to join us on that, hang out with us on the internet, talk about, whatever zany thing you want, you can join us at bimbomentality.freeforums.net. Other than that, I think that is gonna do it for us this week on Bimbo Mentality. Our intro outro music is 10 cents per minute by Tonsil Hockey. If you would like to take your hand and try your hand at thinking like a bimbo, you can send us your pitch. Excuse me. You can send us your pitch on Instagram or Blue Sky. Bye, everybody. See you in a couple weeks.